That is a fine tuning. So how many neurons we require, so that how we can arrange them in proper way. So that is a fine tuning and training process. So if it is a small problem, we can go with 2 to 3 neurons. Like if you are going with uh, XOR operation, exclusive or, for example, the X1, it consists of X1 and X2 and Y. So this is opposite to our hypo. When it is 0 0, output is 1 1 0, output is 1 0 1, output is, sorry, it is 0 1 and 1, output is so 1. So in this case, as if you try any machine learning model, uh, the machine learning model not able to classify this. So minimum, because all machine learning approaches, linear, logistic regression, SVM, random forest, KNN, XGBoost, all machine learning models will be on only a single neuron, will be worked on only single neural network. That is that is like only one neuron will handle all the inputs and all the computations. Only we are going to use y predicted is equal to w naught plus and w1 x1 plus and so on, like that. All the inputs are handled by the one neuron only. Here all the inputs are handled by the multiple neurons in neural network concepts. So whenever it is required more complex data, more in-depth patterns are there. So if it is directly classified without any knowledge, then the machine learning models can do. But if it is having many mimic features, like simple very small features, if you have like face recognition, uh, any image processing type of thing, so we need to extract the small features from the given data. So for that concept we required neural networks, uh, multiple neurons to be solved in a single problem. So this will be first we are given x1, x2, x3 or the input variables. Otherwise, if you are having a matrix, like if you are converted any image to a matrix, a 2-dimensional or 3-dimensional matrix. So this here 4 classes are there: x1, x2, and x3 and x4. Maybe any number of inputs. So this x1, x2, x3 will be passed layer by layer, so row by row it will be passed, and the output will be connected. Based on that, the training process will be done. Here regression classification, the training process completely same, but the thing is we are going to change the output layer and error calculation method in the classification to regression models. But forwarding the network and back propagation all, or any optimizer if you are using now, so everything is same. But the thing is from regression to classification, only how you are calculating the error, how you are calculating the loss, and the dense layer we are taking. If it is a regression, we are going to take only one neuron only will take the output. The output layer will consist only one neuron. But if it is a classification, we need to mention multiple neurons uh, for clearly classifying the output. Like if you have 2 classes, yes or no, or 3 classes, or digit recognition, 9th or 10th classes. So based on that, we need to arrange we need to build our output layer. So only the things from regression neural network to classification neural network, only the output layer and how you are calculating the error, that will be different. First we'll see how a single neuron will work for a given data set. For example, in our data set we have 13 features like x1, x2, x3 and x4, like that. 13 features are there. 13 features are there that will be handled by the single neuron. Here whatever you can take, like is a house price prediction data set, that x will contains these are x1, x2, x3, x4, x13. So x will consist 30 cross 1 means one row, 13 columns, one row. Here the weights, corresponding weights, 13 weights we are giving, but we need to multiply these to x into w, so the dimension will be changed. One row, 13. And the bias for each and every neuron. We are taking only one neuron. So bias is only one we have taken. So actually the equation will be formed y predicted is equal to w naught plus w1 x1 plus w2 x2 and so on. One bias will be sorry, this w naught will be the bias, and remaining will be multiplied, and y is the only target variable, only one we have, so the dimension is 1 cross 1. Here the output is 1 cross 1, bias is 1 cross 1, because only one neuron, this will be the bias. And input 2 4 up to 13 features, and weights also we are taking, that it means each and every, here x1 it is, x2 it is, and x13 will be here, 13 plus 1. So here x1 w1, x2 w2, and w3, here we'll have one more connection w13, this will be w0 is always 1. So in this way, forward propagation, one neuron will be trained, and will get the y predicted value directly. This will not be passed to any neuron, just single neuron training. So here is the how we compute the loss. If it is a regression problem, we are going to take the loss of y minus y predicted whole square. That is the loss we'll calculate in regression problem. And obviously, if we get high loss, then we are going to back propagate it, or we'll change the weights using some optimizer. Like here, if we are taking a gradient descent optimizer, so in that way, according to that, we'll change the weights. So simply. Same way, you can take one more neuron that will be connected to all the inputs, and it will be passed to one more neuron, and it, like that a network will be built. Uh, when regression to classification, if we come to regression to classification, only some parameters will be changed. That will clearly, that will see same problem. In previous slide we applied only single neuron, but here we have multiple neurons. This is x1 input layer, x2, and here it will be x13, and this will be the bias. So here 1 2 3 4 4 neurons are there. 4 neurons are connected to one other neuron, so it will be the y predicted value. This one hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4, and each and every, here 13 inputs are there. They are connected to 4 neurons, so we require 13 into 4, totally 52 weights we required, 52 plus again 4 bias, so totally 56 parameters weights we required to train up to this part. And after that, here we required one more thing, w, like 57, 58, w58, w59, w60, and one bias w61. Totally here 56 plus 5, 61 new weights we required, w weights we required for this network. Our input size is 13 features and many number of rows. So here row by row it will be passed, and corresponding row, for example here x1, x2, and x3. So row 1 will be passed first. Row 1 will be passed. And what is the y predicted, y value, actual value, that will be checked here, and we can compare and we'll calculate the error. Same like a regression, a simple linear regression or SVM regression model. We'll calculate the mean square error, and we'll compute the error. We will update the weights, regression problem. Yes, take the input features, according to that how many neurons you require, or how many neurons we require, that many neurons we can arrange here. This is a fine tuning, means we are not going to take extra neurons, or we are not going to take less neurons. So for the given data set, how many neurons, how we can find out? By adding or deleting some neurons. So if you are going with 2 layers, 3 layers, 4 layers, so which combination or which set of neurons will provide us the best less error, that will we can consider layer by layer. So and we can drop some neurons in while the training process is going on with using dropout layer. Same. Now come to the, as of now we have seen uh, regression neural network, artificial neural network. Now what should we change? What could be the changes for the classification when we come to the classification problem? So here actually what is the data set? We can't implement a classification problem blindly. First we should check the data set. If the target variable, if the y values are uh, what uh, categorical values, or if the y values are qualitative values, then we can go for the classification problems, classification model. We are going to implement classification models. So if it is y value is continuous values, then regression model we. So by checking the data set, once we confirm if the y values are consist of categorical values, then we'll implement a classification model directly. So the labels are like categorical values grouped over some numbers. Now, here in multi-layer or single neuron, how many neurons you took? So single linear activation function will take like x value, y value, whatever it is. So single linear means directly we can implement y is equal to w naught plus w1 x1 plus w2 x2, and this will be the y predicted value. Directly will calculate, no need to convert anything. But because linear data output is also linear, like continuous values will get, and continuous values also target variable. For example, uh, x1, x2, and y 1, 2, 3, 4, 5, 6. So it is a linear equation. If we calculate y predicted values with a single neuron where the outputs are weights are 1 comma 1, the equation will be y predicted is equal to w naught plus w1 x1 plus w2 x2. So we'll get the y predicted value as 4, y predicted value as 10. Here weights are, I have taken 1, 1, 1. X1 is 1, x2 is 2. So 2 plus 1, 3, and 1 more by us, 4 we got. So here target is continuous values, and we'll get the continuous values as y predicted values. So no need to think much. Directly we can calculate the error. Linear output. So how many neurons you took? No problem. Directly that y predicted is the y predicted value. No need to convert, because when come to the classification, we need to check how the y values are varied, whether the y values are changing over 2 classes or 3 classes or multiple classes. Based upon that, we can arrange an activation function. Here the activation function is, it will convert the linear to non-linear, will convert the linear data to non-linear data. So this is very important in classification model. Here if you are taking sigmoid activation function for binary classification, majorly will use the sigmoid activation function is 1 by 1 plus 1 plus e power minus z, e power minus z. So whatever the values, like z is equal to we can calculate w naught plus w1 x1 plus w2 x2 and so on. See, if it is a regression, this will be the directly a y predicted value. But if it is a classification, we are converting this linear data, like continuous data, to categorical one. Continuous data we are converting to a categorical one. So this sigmoid function will give us whatever the values. The input is whatever, minus infinity to plus infinity, whatever the input values, but the sigmoid will convert in between 0 to 1. The output of sigmoid function is 0 to 1. The equation is 1 by 1 plus e power minus z. Z is the continuous value we substitute, and that will take the converted to the categorical values. Thus, this is a sigmoid activation function. Why we are using this? It is for converting the continuous values to categorical values. It means minus infinity to plus infinity values we are converting into 0 to 1. 0 to 1 it will be converted. Why? Because our y values are binary classes. Yes, no, good, bad, 1, 0, like that. Our y values are distributed over 1, 0, 1, 0, 1, 0, like that. So that's why we are taking at last the continuous values we are converting into categorical values with the help of sigmoid equation for binary classification. So we'll get 0, 0.1, 0.2, 0.3, 0.4, 0.999, and 1, like that we'll get. So here above 0.5 we can consider as 1, below 0.5 we can consider as 0. So that's it. This is a basic binary classification problem. Okay, the output layer is, if you are taking one neuron, so if it is a binary classifier, one neuron is enough. Binary classifier, one neuron is enough, because the sigmoid function is giving 0, 1, 2, 3, 0.1, 0.2, 0.3, 0.4, like that values. So if you are only one neuron, that neuron will grab the value 0.1, 0.2, 0 to 0.999 and 1. So if we are getting above 0.5, greater than or equal to 0.5, then that we consider as 1, less than 0.5, that will be considered as 0. So this is a process. Only one neuron is enough for binary classification. But when come to the multiple class classification, so we need to change the activation function, because sigmoid function, as we know, it can give the values 0 to 1. That will not be useful for the multiple class classification. Like if you have a problem on digit recognition, so we are going to recognize the hand digit, like either it is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are going to recognize the digit. For that binary classification, a single neuron is not at all uh, useful. So see, if single neurons, or if it is not a binary classification, then no need of sigmoid function. Remember this, when we are doing binary classification, then we are going for the sigmoid activation function. If it is a multiple classes, 3 class or 4 class or any classes, so we are going for the multi-class classification, and the activation function is softmax activation function. Softmax activation function here, the output layer will be multiple neurons, not single neuron. Output layer will consist of multiple neurons. Let's say uh, this is the input, 3 neurons, 3 features. So upon this we build 4 neurons are connected, like this. 4 neurons are connected, done. All features are connected, and my output layer, this is the input layer, hidden layer, and output layer. This output layer is only one. It means the intention is to, we are classifying only binary, we are having only binary classes. But if you are going to have multiple classes, like you have 3 classes, 0, 1, 2, after converting, after embedding, so then we should take 3 neurons on dense layer. What is the weightage of, for example, here we got 0, here we got 0.1, so we'll get 0.9 here. So according to that, this neuron will representing 0 class, this neuron is representing 1, this neuron is representing 2. That means here we got 0.9 means, so the classification output class is 2. Like that we are going to classify. Let me clear all once I have to clear. Okay. So here I hope you understood, when we took binary classification, when we took multi-class classification, and how many neurons we should arrange, we should keep when we are doing binary classification, when we are doing multiple class classification, when we are doing binary classification. class classification means two classes will be there. So single one neuron is enough at output layer. So when we are doing multiple class classification, multiple neurons are required, and we should change the activation function to the softmax activation function. Binary classification, only two classes like yes, no, good, bad, 0, 1. Only one neuron is enough at output layer, and sigmoid is an activation function. So in between, whatever the activation function we took, but output layer I'm talking about, output layer. And if it is a multi-class classification, we need to take as per the how many classes. If you are going to classify them into 10 classes, so our output layer must consist of 10 neurons. If you are going to classify 10 classes, so we must have 10 neurons at the output layer. And the activation function we should take, final activation function in between whatever it is, final activation function we should take as soft to max activation function, soft to max activation function. This is the important points from regression to classification, the major differences here we are going to take. How many building concept? This is output layer only will we are going to change, not the input layer, not the hidden layers. In between all the layers, only output neurons and output layer only we are considering. We are differentiating from regression to classification, only the thing. And next thing is how we are going to calculate loss for a given problem, loss function. So the loss function selection is also important for the classification. Basically, if you are using a regression model, then our loss function is finally how we are calculating the error or loss. Based on that, how we are going to update the weights, because we are calculating the loss to update the weights. In classification, final results will be exposed in accuracy, precision, recall, but for updation of weights we need to calculate the loss. What many loss functions are there, like Hing loss or cross entropy loss, categorical cross entropy loss. Okay, many loss functions are there according to the problem. According to the problem, how many classes are there in our target variable? If the target variable is regression, what to calculate? If the target variable is classification, what's the how many classes? If it is binary class classification, simple cross entropy error is enough. If it is multiple class classification, categorical cross entropy error or loss we should calculate. Why we are calculating loss? To update the weights. So we are to adjust the weights so that we will try to reduce the error to properly train our model. So as usually, if you are doing regression problem, either linear regression or logistic, SVM or ANN, also if you are doing regression, the loss function is mean square error maximum when used, otherwise mean absolute error or Huber loss will calculate. And come to the classification, if you are doing classification, what type of loss we can calculate? So if it is a classification, the loss function is binary cross entropy, binary cross entropy only. Means loss will be calculated in between actual values to predicted values. What is the actual value and what are the predicted values? In between, the differences will calculate, the error will calculate. Based upon the error, will change our weights. So if it is a binary class classification, so binary cross entropy will calculate. The equations I will show in next slide. And if it is multiple class classification, we are going to calculate categorical cross entropy loss. A small difference is there in between binary cross entropy and categorical cross entropy loss function, a small difference. And these are the loss function. These will be used for updating the weights, adjusting the parameters, adjusting the artificial neural network parameters. We are forming an equation for each and every neuron, like WP YP is equal to W naught plus W1 X1 plus W2 X2. Like that, we'll form an equation in that W values are unknown. Actually, that is our target. We need to identify the W values, for which W values the error, the loss is minimal. For which W values the loss is minimal, that W values will tune. That W values are final weights. So to change the W values, we are going to change. We are going to calculate the loss in between, loss in between y values to y predicted values. This is like error calculation for weight updation or parameter tuning. And next thing is, okay, evaluation metrics, how you measure the performance. How you measure the performance. Same, uh, even we can take mean absolute error between. So mean square error we use for updating the weights, but uh, and mean absolute error will take for evaluation the metric. For example, you trained a model with 3 layers, each layer with 842 neurons, like first layer 8 neurons, second layer 4 neurons, third layer 2 neurons, and one output layer. So according to this, so if you are doing a regression problem, so we generally will say, I have trained a regression model, artificial neural network regression model, and my error is so and so. I got an error up to this, how much this. So in this way we can scale it. Performance of the model we can measure with the mean absolute error or root mean square error or r square error. We can also use mean square error also for this, but both mean square error can be used as a loss function and evaluation metrics for both. When we are doing regression problem, when we are doing regression, then we'll use uh, mean square error as a loss function, otherwise mean absolute also we can take, and mean absolute error as for evaluation type. And when come to the classification problem, how we can measure the performance of the given model, so with this, accuracy, precision, recall, F1 score, and confusion metric, these are the basic basic metrics, basic measurements for classification model. So if these also will be calculated in between actual values to predicted values. Actual values to predicted values will calculate the accuracy, will calculate the precision, recall, and F1 score. From that, we will calculate the confusion matrix. So this is the basic evaluation metrics for classification. Here, accuracy will be calculated. For example, actual value is 1, predicted value is 0, and actual value is 1, predicted value is 1, actual value is 0, predicted value is 0, actual value is 0, predicted value is 1. So here, total number of samples are 4. Total number of samples are 4, 1, 2, 3, 4. But a model correctly classified out of 4, 2 correctly classified, so we can say the accuracy is 50%. And it is a binary classification only. It is a binary classification because only 2 classes are there in our data, only 2 classes, that is 1 and 0. It is a binary classification. So for this, loss function will be used, cross entropy loss, and the activation function will take as sigmoid activation function. From this, we can build the confusion matrix. So it is a 2-class classification. So our matrix size will be 2 cross 2. 2 cross 2 will take from this actual, I'm taking actual 0, actual 1, predicted 0, and predicted 1. From this side, y predicted, and above actual value. So actual value is 1 and predicted value is 0. So actual value is 1 and predicted value is 0. That is happened only one time. And actual value is 1, predicted value is 1. That is also happened one time. And actual value is 0, predicted value is 0. That is happened one time. Actual value is 0, predicted value is 1. Actual 0, predicted 1. This is here 1. So all thing we have in our, this is our confusion matrix. From there, we'll calculate precision of 0, precision of 0 class, precision of 1 class, precision, recall of 0 class, recall of 1 class, all the classes will calculate. This is for after training, after updating the weights, after doing everything. So finally, we'll use this accuracy, precision, recall, F1 score for the as an evaluation metric to show the performance of the model. Okay, and basically when we'll do classification based on the output type for the given data set, Either classification or regression comes under supervised learning model, supervised learning. So when we are saying supervised learning means there must be a target variable. If the target variable is having has continuous values, if the target variable has the continuous values, then we can go with uh, regression problem. If the target variable has categorical values, then we can go with target variables are uh, group values or categorical values, then we can go for the classification. Either if they are repeated over two classes like 0, 1, then we can do binary class classification. Or if they are repeated over more than two classes, then we can do multi-class classification problem. This is the way. When we can move on to the ANN classification based on the output type. Okay, what are the output type? Continuous and categorical or discrete values. So how we can build a neural network? Everything is same, input layer and hidden layers are same, but we are going to change only the output layer. Output layer. If it is a binary classification, the output layer consists only a single neuron, and the activation function of that neuron is sigmoid. In between, whatever the how many neurons you want, that many we can take. And uh, activation functions also not important. Any activation function we take, either no activation function or yes activation function, tan h, relu, rectified linear unit, softmax, sigmoid, whatever the activation function we can take in hidden layers. But when come to the output layer, and if you are doing binary class classification, the output layer must and should contain only one neuron, and that neuron must contain the sigmoid activation function. Okay. If you are doing multi-class classification, so how many classes you are doing? Like 3 classes or 4 classes or 5 classes. That many neurons we need to add at the uh, end layer, output layer, and the activation function must be softmax activation function. So this is the building of neural network. So after this, three changes. Loss, how you can calculate the loss? Basically we'll calculate the loss for parameter changing. Parameter value changing means weight updation purpose will calculate the error. So weight updation purpose will calculate the error. So what type of error we should calculate? When come to the regression, we'll calculate mean square error or mean absolute error. When come to the classification problem, again two types of errors we can calculate. If it is binary classification, cross entropy. If it is multi-class classification, categorical cross entropy error or loss, we should calculate. The second difference between ANN regression to ANN classification. And same thing, evaluation metrics also same from machine learning models, and we'll see other differences. And what are the activation functions we can take in between hidden layers? What are the activation function? Whatever we can take. These are the common points. Value you can take, tanh you can take, any activation function you take in between input layer to output layer. That is activation function. And some use cases, some example problems like house price prediction is a regression problem. You can build a machine learning regression problem or neural network regression problem like stock price prediction, temperature estimation, phone price prediction, car price prediction, wind speed prediction. So these all comes under the regression problem. But when it comes to the classification, disease diagnosing, health disease or sick or any tumor classification or image classification, okay, good customer, bad customer, sentiment analysis. So these are the sentiment analysis. Maybe if you are going to classify good sentiment or bad sentiment, understood? Good or bad, only two classes. So it is a binary class classification. Otherwise, sentiment mean angry, happy, like that. Then multiple class classification problem it is. So like that means output values, based on the output values will build our neural network, and based on the output values will do calculate the loss, and based on the output value will update the weights and will arrange the activation functions. Again, one more difference is that, so okay, we fixed that, we thought that we are doing classification, and what it is, what type of classification, whether it is binary class classification or multiple class classification, multiple classes. So here the classes are either zero class or one class or two classes, like good, bad, or average. Good, bad, or average. So here, yes, no, or 0, comma 1. Binary class classification and multiple class classification. So what we can do, we'll see the differences between binary class entropy loss and categorical class entropy class. So we can check use case. When binary class means only two classes, as I given the example, yes, no, like good, bad, fun, 0, true or false. In these cases it comes under what? Output values, target values. If the target values are repeated over two classes, two values. If the target values, y values, are repeated over two classes, two values, then we'll take binary class classification. If the output values, if the target values, or if the y values are repeated over multiple classes, like 0, 1, 2, good, bad, good, bad, average, then it is comes under multiple class classification, and like classifying a digit like 0, 1, 2, 3, 4. It is also multiple class classification problem. So output layer, how many neurons we can add at the end? Same binary class entropy, one neuron will take. And remember that, as I said, sigmoid only the activation function, because sigmoid is blindly we can use it for binary class classification. And multiple neurons we will take for multiple class classification, and the activation function we will take as a softmax activation function will use. And labels of cross entropy, binary cross entropy labels mean y values. So whatever the y values, like if you have good and bad, we will encode them into, convert them into 0 or 1. Okay, male female, like 0 1 will be convert then in that case. But here we'll do one hot encoding process. What let me give one example. If the y values are 0 1 2, 0 1 and 2. Okay, and the y predictor we can write as one hot encoding process. One hot encoding means 0 1 2, not a binary class, so we'll convert them into indirectly binary classes. Like this is the 0th class, 1 class, and binary class. So here it is 0, here it is 0, so we'll put 1 on 0th place and remaining all zeros. So if it is 1, the encoding process is like 0 1 0. If it is 2, the encoding process like 0 0 1. Again, if it is 0 1 0 0. If it is 1 0 1 0 0 0 1. So in this way we can convert the given output values into one hot encoding for multiple class classification. Understood? One hot encoding we should do. Example is, example problems are heart attack prediction, yes, no, binary classification. Okay, skin disease prediction, yes, no, and spam mail detection, yes, no. Otherwise, skin disease detection, what type of disease is no. Uh, Multiple classes will be there, so it is multi-class classification. Like dog is class 1, cat is class 1, dog is class 0, bird is class 2, like that will do. And especially we have discussed for binary cross entropy and categorical cross entropy. Binary cross entropy function, and this is categorical cross entropy function. So we know binary class entropy function is used for binary class classification. Categorical class entropy function is used for multiple class classification function. Let's like this is, we'll take an example. Y is equal to 1 0 1 0. The y predictor values here in this function, the y predictor will be calculated from a sigmoid function like 1 by 1 plus e power minus z. This will give us the values in between 0 to 1. They are like 0.5, 1, 0.02, I said 0.4, that's 0.5. So these are the y predicted values through sigmoid activation function, and these are the y values. Just substitute in this, we'll get a mean loss. Mean loss here, output size is 4. 4 samples are there, 4. Here this will be the actual value. Actual value is 1 into log of y predicted value. Y predicted value is 0.51. So log of 0.51 plus actual value is for all. This is for this first row I'm substituting. Actual value is 1. So 1 minus 1, it will be 0. This term will be cancelled. Okay. Now in this binary class classification, we are going to take the log difference between the actual values to predicted values. Actual values to predicted values, we are calculating log difference. Okay. If it is 0, if it is 1, we are going to calculate log of 0.01. The loss function is log of 0.51. Okay. If it is 0 comma, if the y value is 0, so if the y value is 0, actual value is 0, so 0 into something will be 0. And what we'll do, second part, 1 minus 0 into log of 1 minus 0.02. So we'll get 1 minus 0 is 1 into log of 0.8, log of 0.8. This is the log value, or we can say log of error. Then all mean will take, that is the log loss error or cross entropy error, binary class entropy error. This is log. In this way we'll calculate. Just a second. Yeah, is my screen is visible?
Yes, sir. Yes, sir.
Okay. So this is the example for binary class classification. Cross entropy loss only will calculate. After cross entropy error, after calculating, then we'll change the according to the loss, whatever the loss we got, according to the loss we'll change our weights. And after fine tuning, after repeating some number of times, we'll do what? We'll calculate the accuracy, precision, recall, and all everything. After finally when we confirm that the loss will not be reduced at all with this neuron, so we will check the performance by calculating error. So as of now, if it is binary class classification, this log error or binary cross entropy error will calculate. And when we are having multiple classes, categorical cross entropy error will calculate. Categorical cross entropy error will calculate when we have multiple. Same, this is same like log function or binary cross entropy loss. 1 by n is the number of samples, and this is by number of rows, and this is the number of classes. This loop will be repeated over classes. Each class means 0, 1, 2, 3. For each class will calculate, and each row dimension, row and column wise it will go. In a two-dimensional way we are going to calculate, because as of now only one value we have taken. So if we clearly observe this equation, if you clearly observe this equation like which I highlighted, y into log of y predicted plus y minus y into log of 1 minus y predicted. So if our y value is 1, y value is 1, so y predicted value is something like 0.8, then we are going to compute this one only, because 1, if you substitute here 1 minus 1, it will become 0. Means when y value is 1, we will compute this loss. When y value is 0, look at here, if y value is 0, we'll substitute here, so this part will become 0 and this part will be highlighted. 1 minus 0 means 1 only. Log of this part will calculate. Understood? So here when we are doing binary classification, though we have two classes, like 0 and 1, 0 and 1, though we have two classes, but at a time we are considering only one class only. At a time we are computing only one class, so that is written here every time. Okay, here what is the actual class? For example, y value here is 0, 1, 2. These are the y values, and y predicted, I already said y predicted is converted into 0 class. It is a three class classification. The three classes are 0, 1, 2. What? Actual values. And y predicted, sorry, this will be converted, encoded. First encoded, no y predicted values. This is encoded, one hot encoded. 1, 2. Now this we can write as 1, 0, 0, and 0, 1, 0, 0, 0, 1. This is the y value after one hot encoding. Now we'll get y predicted values. How many? Here, if it is a binary class classification, only one neuron will take at the output layer. But if it is three class classification means a dense layer or output layer must contains three neurons. Or output layer must contains three neurons. Neuron 1 for class 0, neuron 2 for class 1. This is for class 0, class 1, and class 2. So whatever the hidden layers in between this. Okay, this will be the class 0 value, class 1 value, and class 2 value. So what we got? For class 1 we got 0. This is 1. Sorry, 0, 0. Yes. Oh, this is 2, correct. Yes. For class 0 we got 0.6. Here we got 0.3. Here we got 0.1. Let's take we got these values, each neuron output value. Neuron 0 output value is 0.6, neuron 1 output value is 0.3, neuron 2 output value is 0.1. So how we'll calculate now? Here first, this is the target value. Forgot about this. Now, this is our y value, and this is our y predicted value for this row only. Thus this row. Yeah, this one. So actual value is 100. 100 we got as 0.6, 0.3, 0.1. Now we'll calculate the loss as 1 class 0. 1 into log of 0.6. Okay. Next, actual values. So here the output value is 0, and here we got 1. So y value is 0, and this one is log of y predicted is 0.0, 0.3. It will be done 0, and this one is also 0. This one will be 0. Like what will we get? Log of log of 0.6. Here we'll get, this is the first row error. First row error will calculate like this. Same function but simplified into with the summation. So in this way, we are going to calculate the categorical cross entropy loss function. You can simply observe here, whenever the actual value is involving here, if it is a zero class one, and here is a zero class one log error only we are taking, means that difference only we are taking. Remaining differences we are not considering. Like what is the difference between this value to 0 to 0.3 or 0 to 0.1, that difference we are not taking in class entropy error. Understood? Whatever the actual class is 0, and predicted class 0th class probability value, that only we are taking, and we are finding the log error. This is the categorical cross entropy loss. Anyway, from binary classification or categorical cross entropy error, we are going to calculate the log differences between particular class, which class we are taking. Like either it is a class 1, so that difference only. Actual value is 1, so predicted value is what? So that difference only will calculate. Actual value is 0, and 1 minus 0.0, we will take that. 1 minus log of 0.1 minus y predicted value is like that. This one log of 1 minus y predicted value. This is for a binary cross entropy. This is also same thing we took in uh, multiple class entropy function. That is, what is the actual class? So basically in multiple class classification will convert into encoding, one hot encoding, like 1, 2, 3. So that will be converted, y value will be converted into 1 class, 2 class, 3 class. So this is a major thing we need to do in uh, multiple class classification. 0, 1, 0, 0, this one, 0, 0, 1. This is the y value, and so if the y predicted values, we have in our next slide. Okay, this is a feature 1, feature 2, x value, x1, x2, and it is a y value, and these are the y predicted value. Okay, so if it is here we have true classes are 0, 1, and 2. The multiple class classification, directly 3 class classification: 0, 1, 2, 0, 1, 2, 3 class classification. Here what error will calculate it for this? Will calculate for this. So what error will calculate? It is a actual value is 0. So what we should take? Log of this is a 0th class, this is 1, and this is 2. That value we will take only log of 0.7. That's it. This log of 0.7 is the loss of that row. And second, the y value is 1. It is comes under second class. Second class means this one, second class. So here the error will be computed as log of 0.8. That will be this one. So remaining will be 0. Remaining will be null, and it is a third class. This is a third class. So how we can compute the error? Loss log of again 0.8. In that way we'll compute the loss. And here again y value is 1. So this is 1 class. Log of 0.7. 0 is, so first one. Log of 0.6. This is the row wise error we'll get for cross entropy loss. What? Multiple class classification problem it is, and cross entropy error will take all mean values, so that mean error or mean loss will get. Based upon the mean loss, again we'll compute the weights. We'll update the weight. This is the multiple class cross entropy loss function. Even in binary class also, if you clearly observe, it will be look like same. Here, once again, I will take the example y value, y predicted value. Only binary class now, only one neuron will take, one neuron will take, and the sigmoid activation function will take only one neuron. So for example, if the output value is 1 0 1 0 and we predicted all ones, sorry, like it is sigmoid function now, may get in between 0 to 0.9 and it is 1, this is 0.8 and this is 0.7 like this, 0.7 like this. Now if we compute the loss, for this, so just observe, just look at y value for this row, will compute the loss for this row. Y value is 1, so y value is 1 into log of what is y predicted, it is 0.9 and plus 1 minus what is y value, 1 minus 1, so it will be 0. So what we are finally doing, log of 0.9, that's it, log of 0.9 minus this minus I took, log of 0.9. This is the loss of binary class. Now here what we can take, which function will be computed? Here the actual value is 0, so if you substitute 0 here, this will be done, null, and 1 minus 0 into log of this 1 minus, and y predicted value is here what it is, 1. And for this, log of directly 0.8, and for this what, log of 0.3, because 1 minus 0.7, so minus 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 minus. This is the, in this way we'll calculate the loss of a given function, loss of a binary class classification, So here we will take only one neuron. I hope you understood. What is the use of that one neuron? That will be taking the values every time, one value only we are considering. If the based on the actual value, if actual value is one parameter, if actual value is 0, second part will be considered. And if it is multiple class classification, what? How many classes are there? That many neurons we are going to take. For example, if it is a 3 class classification, so what will get? 3 class classification now. 3 neurons will get, neuron 1, neuron 2, and neuron 3. And these true classes will be divided into 0th class, 1 class, and 2 class for easily understand. So if it is 0 now, so it will be encoded into 1 0 0. Next 0 1 0 0 0 1, third row, and fourth row is 0 1 0, fifth row is 0 1 0 0. This is the 3-dimensional one, and 3 neurons we are taking. That's why each neuron will give us some output. So in this case, you can take same. The class is this one, 1 0 0, y of log y predicted value. First row we are taking, first row j value, like I value is 1 here, I value is 1 my first row, and j value will be for 0th class, 1 class, and 2 class. So here y101, 1 into log of y predicted is what, 0.7. Next plus y is what, 0 into log of 0.2 plus 0 into log of 0.3. 1. Understood? This one will become 0, and only this is log of 0.7. This will be log of 0.8. See, always not 0.8 ma. For example, not the bigger value. You can get if it is one value now, so it will be middle class. So that value only will take log of 0.8, and class 2. Class 2 means this one only log of 0. Log of 0.8 will take. And for first class 1, so it is middle one, log of 0.7. And if it is 0 class, log of 0.6 will take. Now I'll get positive values because by default minus log will compute, and so mean of this value will be the mean loss of that neural network. Why I'm specifically concentrating on output layer only, because either regression or classification or multiple class classification or binary class classification, only the difference is the output function. Only the difference is output function. That's why that's how many neurons you are taking at output layer, and if you are taking one neuron, what is the activation function? If you are taking multiple neurons, what is the activation function you are taking? That is only specifically concentrating for classification. And after that, this is a building concept. After that, while you are training, how you will compute the loss? How will you will compute the loss? Either binary class entropy loss or categorical cross entropy loss. So which one will compute? Binary means one type of a loss will calculate. Multiple classes means one type of loss will calculate. And then that is a basic difference between the regression, classification, building. Understood? In classification, again, binary class classification, multiple class classification. So major differences between regression to classification, and how we can implement the model, how we can implement the implementation. So this is the model we are building. This is the model we are building sequentially, means layer by layer. So we are taking a dense layer. Dense layer means it will be fully connected, and inputs it will consist of 8 neurons, like 1, 2, 3, 4, and so on up to 8 neurons. And what is the input dimension? For example, if you have only three features in the sense x1, x2, and x3. So here I'm writing x1, x2, and x3. X3 shape of that one will be x1, x2, x3. That will be connected to 8 neurons. 8 neurons. How? Densely. Densely means each and every neuron will be connected to each and every input will be connected to each and every neuron. So here 3 inputs and 8. 3 8s are 24 weights we require. 24 plus for each and every neuron, 1 bias. So totally 32 parameters we need to fine tune. And when very important thing is activation function you are using. Activation function you are using is ReLU activation function. ReLU activation function. So if you are going to take one neuron separately, it will have x1, x2, x3, and only one neuron I'm taking. One neuron, it will take three inputs, one bias, so it will compute z is equal to b or b plus w1 x1 plus w2 x2 plus w3 x3. This is our w1, this is our w2, this is w3. So z value only will compute. This is our z value. Okay, now what we are doing, we are taking ReLU activation function, ReLU of z. This ReLU will convert the linear data to non-linear, like continuous values to categorical data. So here we'll get one value that will be passed to either output or another neuron. Now this is a one neuron operation in a neural network. So initially take random W values and compute the final. Next, what I did for the same model, I have added one dense layer. Yeah, one dense layer with 6 neurons. Means here in the first I took 8 neurons, and next layer is 6 neurons. 1, 2, 3, 4, and here is 5 and 6. How they are connected? How they are connected densely means these 8 neurons will be connected to fully. One out of 8 will be connected to all 6 neurons. So it will be fully connected. Same. So number of connections will be 8 into 6. So totally 48 connections will be trained. 48 weights, 48 W values plus 6 bias we required. So 48 plus 6, 54 weights we need to update in this layer. This is a one more layer, and one activation function is again relativity. That is our wish. Whatever the activation function we can take. Uh, relieve or tanh or any activation function we can take. And next third dense layer, this is will be the output layer. Now dense layer will consist of 3 neurons means 1, 2, and 3. So how they are connected? Densely, fully connected. All 6 neurons will be connected to 3 neurons. So it will be like this. Like this. All three. Layer 1 with 8 neurons, layer 2 with 6 neurons, layer 3 with 3. That is a dense function, and no more layers are there. Maybe this will be the last layer. And here you can observe activation function is softmax. Here the activation function is softmax. Activation function is the softmax. So the 6 is connected to 3. So totally 6 3s are 18 plus 3. For example, here I'm writing layer 1. Okay, 8 neurons. 8 neurons. What is the input? Input is 3. Input is 3. Totally 8 3s are 24 plus 8 bias. Next, at layer 2, 6 neurons we take. For these 6 neurons, 8. This one will be 48 plus 6 weights. Next, layer 3, the last layer, it consists of only 3. And this one, 6 neurons output it will take. So 3 8s are 18 plus 3 neurons. So these many parameters, 28, 24 plus 8, 32. This one will be 54 and 21. So 21, 32, 53, 53 plus 54 is 107. Totally in this 107 weights to be updated. 107. 107 weights to be updated for each iteration. For each iteration, 107, 108, almost 107 weights means parameters we need to train, we need to update and correctly classify the given output. And if you observe here, the last layer will consist of 3 neurons only, means we can say that from this it is a multiple class classification problem. Multiple class classification problem. So for that, what we need to calculate? The loss we need to calculate as categorical cross entropy loss. Loss we need to calculate as categorical cross entropy loss. So and what optimizer we are using? Adam optimizer. This is for changing the weights. What 107 weights will be changed based on the Adam optimizer, or any weight updation, any optimizer we can use to change the weights, to update the weights. Model.compile. This will be the compile, and how you are measuring the performance. The performance metrics will be the accuracy. First iteration, feed forwarded, and loss will be calculated, and accuracy will be calculated. Loss is used for updating the weights, and Accuracy will be used for just showcasing, means we got this much accuracy. So just measuring the performance, but loss mainly used for weight updation problem. I hope you understood. This is a theory part of binary class or multiple class classification of ANN. Hello, sir. Any doubts you can ask me.
Ramesh sir,
Yes, sir.
you
Break,
called, na?
break,
Okay, okay,
break.
fine, sir. Yes. Can we take break now, sir? Is it okay?
Okay, sir.
Participants, now you can take a break. Now it is at 3:15. You can take a break up to 3:30 and please join at 3:30 p.m. for the day 4 session 2. Thank you. Take a break up to 3:30. Ramesh sir.
Sir. Hello, sir.
Call if possible.